Now, we are going to look at how directories are structured in operating system using a tree-like hierarchy. At the top, we see the root directory. It includes 3 directories: spell, bin, and programs. From these 3 directories, the branches extend to the second-level directories, then third, and so on. Our focus is on how paths are defined and operations are performed within this structure. Let's talk about path names first. We have 2 types here: absolute path and relative path. Assume that mail is our current directory and first is our target directory. An absolute path like spell, mail, PRT, first starts from the root and specifies the complete path to a file or directory. The relative path, such as PRT, first starts from the current directory, which in our case is indicated by the current label here, pointing to mail. Moving on to operations, if we are in the mail directory, creating a new directory called count would be done using the mkdir command, highlighted here in red. On the other hand, deleting the mail directory would remove the entire subtree rooted by mail, effectively deleting all subdirectories and files within it. Lastly, this structure allows for efficient searching and grouping capabilities, as elements with similar properties can be grouped under the same parent directory, aiding in organization and retrieval. In this slide, we are exploring the concept of acyclic graph directories in operating system. This structure is a bit more complex than the tree-structured directories we have looked at before. Firstly, notice that in an acyclic graph directory, there are no loops. This means a directory cannot contain itself, either directly or indirectly, which prevent endless loop during directory traversal. One of the key features here is the ability to have shared directories and files. This is incredibly useful for cooperations projects where multiple access points to the same file are necessary. For example, the count directory here is shared between DICT and spell. Another important aspect is that a file can have multiple obsolete paths, which leads us to a critical question: when does a file actually get deleted? It's not as simple as just removing the file or the link. If DICT were to delete a file in count, we would end up with a dangling pointer as shown here. The solution to this problem is reference counting. A file is only deleted when its reference counter goes down to 0, indicating that no link to the file remains. Understanding how this directory structure manages files and directories is essential for any operating system's file management. It ensures data integrity and prevents common errors such as lost files or memory leaks. Here, we are going to introduce a more complex directory structure known as the General Graph Directory. Unlike the tree and acyclic graph directories we have studied, the General Graph Directory can contain loops or cycles. It means that a directory can potentially reference itself, either directly or through a series of links, which could lead to an infinity loop when searching through the directory. The reference counting, our previously discussed method for deletion, fails in the presence of cycles because it can never reach 0 if a file is part of a loop. So, how do we handle these cycles? We use two main strategies. First, garbage collection. This is a process that periodically runs to check whether any files have no valid reference pointing to them. When it finds such files, and only then, it deletes them and frees up the disk space. Second, cycle detection. This algorithm is executed when a link is created. It checks for the possibility of creating a cycle and prevents it, thus ensuring that the system remains free of loops that could cause problems. These methods are crucial for the maintenance and efficiency of file systems that use general graph directories.